Hi, my name is Héctor Vives. I'm an astrophysicist at the Center for Astrobiology in Spain. And many astrophysics departments in research centers around the world have what we call a weekly journal club, in which we analyze some preprints of papers that came out the week before or recently to discuss among ourselves. So, a few weeks ago, this paper came out with the title Don't Forget to Look Up, in which the authors analyzed the possibility of destroying an incoming asteroid of 10 kilometers in size with only a warning time of 6 months. So, of course, both the title of the paper and the situation are heavily inspired by the Don't Look Up film, which came out very recently. And these characteristics of the impact, especially the size, is very similar to the situation we had on Earth 66 million years ago, when all non-avian dinosaurs went extinct by a comet or asteroid impact. So it's a situation in which we have a lot of data of the destruction such an impact can cause, and a situation we really want to avoid happening again. So the authors, this recent paper seems to be kind of a way to call attention to a method they had devised for really low warning times when an asteroid impact is confirmed to happen. So the method, they call it pulverize it, PI for short, although I suspect they call it pi because this is the aspect of the technical paper describing it in detail. And there they analyze, they have a website linked on the paper at the end, which they have all these diagrams, and they describe the main effects that an asteroid impact, even if it doesn't reach the ground, the damage it can cause. It could be due to the shock wave, blasting buildings or people, windows, and everything. The optical flash can be intense enough to start fires or burn things. And also the dust production as the comet or asteroid disintegrates in the atmosphere and settles. It can have climatic effects. So what they propose with their method is to destroy the incoming impactor by sending to space an array of penetrators that would use either the kinetic energy of the impacts or conventional explosives to disrupt the incoming asteroid into smaller pieces of less than 50 meters wide. This size is chosen because at those sizes the atmosphere can act as a barrier and it would be able to deal with incoming impactors with not a lot of damage to the ground. So their key way in which this works is, instead of having a very big shock wave hitting the ground, you will have several shock waves from every different fragment, and they would not be correlated. So you will hear like a lot of thunder sounds spreading out over a few seconds, maybe, instead of one big shock wave hitting everything. The dust production would be very similar, however. So in their method, they kind of try to find an equilibrium of how much would you have to disrupt the asteroid, how much time in advance before the impact and such. But this method is devised for situations in which it's already too late to deflect it. And yeah, the impacts they were talking about in the technical paper for the pulverized method are up to a few kilometers only, but the situation for this new paper, which is an expansion, reaches up to 10 kilometers. Why this size? Well, This is a chart of the diameter of the asteroid, assuming a density of 2.6 grams per centimeter per cubic centimeter, which is more or less what a rocky asteroid would have. And here we could uh, point out several examples. If you remember, in 2013, over Chelyabinsk in Russia, there was it wasn't a meteorite. Well, it was a meteorite because some fragments reached the ground, but an about 15-17 meters asteroid reached the atmosphere, burned up. There were a lot of dashcam footage showing the trail from many angles. And then, yeah, a lot of people came out of their buildings to watch the trail because it remained there for several minutes. However, 2 minutes after the bolide, the shockwave reached the ground and destroyed a lot of windows, and more than 1,000 people were injured by this by this shockwave alone. This was about 20 meters, and yeah, the impact energy was about 1 megaton, which is already the equivalent of a big nuclear bomb nowadays. Uh, in 1908, there was another incident in Tunguska in Siberia, in which an impactor about could have been 50 meters wide. It didn't seem to reach the ground. Looked like it exploded in the atmosphere, but the shockwave of this explosion and the fireball it generated destroyed 2,000 square kilometers of forest. It flattened trees in a really large area. And this is like less than 100 meters wide. It's about here. So it is estimated that the impact energy was between 3 and 30 megatons only. If we go to asteroids of a few hundred meters in size, we reach energies equivalent to, they start to match the entire world nuclear arsenal, like detonated at once. So these lines I haven't said, this is if the impact happens at 20 kilometers per second. This is at 10 kilometers per second. This is 40 kilometers per second and 60 kilometers per second. So it would be around this energy. The asteroid Bennu, it's more than 400 kilometers, 400 meters in size. It's been sampled by a U.S. space probe. We are taking material with it, but it's another asteroid that will come close to Earth, and an impact from that is also in energies equivalent to the entire world nuclear arsenal. But this is just a few hundred meters in size. The 10 kilometer size asteroid would have energies way beyond what we have the capability of inflicting. So the nature is much efficient at creating destruction than we are. However, we are lucky because the higher the diameter of the asteroid or the impact energy, the more time it takes between impacts to happen. So bigger asteroids are less common than small asteroids. And they have a chart on all the measurements of fireballs and impacts that we've had, and estimations from the number of asteroids we see in the solar system and such. And it looks like it's a logarithmic scale. So the really tiny fireballs we get like in years, like 100,000 a year, thousands if they are very big, but just fireballs. Now if we go to 1 meter, or let's say 10 meters, it's about one every 10 years we get one of those. 20 meters it's decades between one of each, like the Chelyabinsk one. 100 meters is already more than 1,000 years between impacts. and 10 kilometers is about 100 million years between each. However, the last one that we have a record of is already 66 million years ago. So if you roughly have one every 100 million years, it's not a completely neglectable threat. Even though really smaller ones, the ones for which the pulverizing method was really devised, are much more common. But yeah, a 10-kilometer asteroid will have truly catastrophic consequences for life on Earth. In fact, I recommend a video by the channel Kurzgesagt, which is the German word for in a nutshell, in which they have a really cute animation but showing all the horrifying consequences of this asteroid impact. I'm gonna link to it maybe in an annotation and in the description. But yeah, for such a big asteroid, the initial method that they proposed using the kinetic energy of the impact of the penetrators or conventional explosives is not gonna work. You need, here the atmosphere cannot deal with all the fragments and still have the world be safe. So most fragments for an asteroid of more than 1 kilometer in size should miss the Earth completely. So the energy you need to give them, it's higher and it's a lot more mass. So you're gonna need nuclear explosive devices for this to work. So here they have two more charts in which you have the size of the asteroid. We are 10 kilometers in size. This is the energy required to disassemble it in joules and in tons of TNT. This is 1 kiloton. So by the way, the Hiroshima and Nagasaki nuclear blasts had a yield of around 20 kilotons only. So it would be around here. We would need more than 1 megaton to have the fragments of the asteroid deflected by 1 meter per second at infinity. So once they've gone far away from each other, they will be going at a limited speed, in which it would be 1 meter per second for this line, 5 meters per second for this one, 10 meters per second for this one, and so on. So if we want the fragments to be moving at 1 meters per second after they have already exploded, you would need several megatons of explosive energy delivered to them. We might require 5 or even 10 meters per second, which gives it even higher values for this. And if it was a small asteroid, most of the energy would just go into giving the speed to the fragments, and that would be it. But with 10 kilometers, already the gravity of the asteroid itself has a non-negligible effect. So at the start of their movement, they would need several meters per second already just to escape each other's gravity. So for an asteroid of the rocky composition, which is the red line, for 10 kilometers you already need about 6 meters per second, just so when they reach infinite speed, infinite distance, if it was possible, they would stop. So the minimum energy, the escape speed for the fragments, requires the energy enough for them to move at 6 meters per second. Of course, if the asteroid has more iron or is more dense for some reason, you would go like 7-8 meters per second. If it's a comet, the same size, but made mostly of ice, you would need like 4 or 5 meters per second given to the fragments. So yeah, you need quite a big amount of energy for this to work. And yeah, of course, as the caption of the plot says, if you needed the fragments to move at more than 100 meters per second and the asteroid was 15 kilometers in diameter, not even the entire nuclear arsenal of the entire world would suffice for this procedure. So yeah. And yeah, one question they address in the paper is like, why cannot the Earth simply just absorb the energy of the bolide like it does with the smaller ones? Like, can we just let the atmosphere stop the asteroid and let the energy? Why do we need the fragments to avoid Earth completely? Well, so even if we fragmented the entire asteroid in fragments less than 15 meters in size, you would still get the shockwaves from all these impacts, which would be a lot of impacts, the optical pulses from all the asteroid burning up in the atmosphere, which are much brighter than many films show. So if you see real footage, like for example, like Chelyabinsk dash camera footage, it is brighter than the sun, and it was just a 20-meter asteroid. So it's not like you can look at the asteroid with just a bit of smoke moving slowly through the atmosphere. The brightness alone would burn you, would blind you. And the dust production in the atmosphere from the burn-up of all these fragments from a 10-kilometer wide asteroid would cause like a nuclear winter effect. So yeah, not only that, but all this friction from the atmosphere, from all the heat, all the energy delivered into the atmosphere from the atmosphere stopping all the fragments, will heat the atmosphere a lot. So the amount of heating of the atmosphere just from these tiny fragments hitting it, it would be lethal. We'll talk about this with a later plot. But yeah, we need nuclear penetrators for this to work, and the paper studies two cases. In the case of fission nuclear bombs, they would be good if they need to penetrate a certain amount of meters inside the asteroid before exploding. However, the yield they have per warhead is not enough. So if we had only 6 months of warning, the speeds required for all the fragments to miss the Earth means you would need to impart like 10 megatons of energy to the fragments so they miss Earth. For 10 megatons of energy to be delivered into the speed of the fragments, you need about 10 times more in margin, because you cannot guarantee that all the energy is gonna go there. Some of the energy is gonna produce like light. Some of the energy is gonna be used to break the asteroid. So not all of it is gonna go into the final speed of fragments. So this means, for the calculations they do with the current designs of warheads, we would need 50,000 warheads to deliver the 100 megatons of energy to this asteroid for this to work. So this is unfeasible. So now they turn to thermonuclear devices, which use fusion reactions instead of just fission, because they have a higher yield per the mass of the device. So 1 kilogram of warhead gives you 4 kilotons of energy, which means that for the 100 megatons you need, it would mean 25 tons, metric tons of mass delivered to the asteroid, plus all the extra hardware, because those devices will have to maneuver, they have to have the targeting systems, guidance systems, and everything to reach the asteroid with the precision needed and all the positions they would require to be in for this to work. So it might be double the mass, but it's not really a huge amount of mass like in the case of fission devices. However, the impact, the penetration impact in the asteroid is so fast that fusion devices, as currently designed, uh, cannot withstand it. So they will be destroyed instead of detonating properly. So they say this requires either new types of nuclear devices, because for fission devices there are some existing ones that are designed to destroy bunkers. Like first they would penetrate and then they would detonate. So it would require either designing new warheads that are capable of this, which you cannot test because this would be like a really big threat to other nations, and there are treaties banning these tests for good reasons. Or you would need sequential penetrators. So you would need to have conventional, like maybe using the kinetic energy or conventional explosives, to first kind of dig the holes for then the nuclear devices to go in and explode at a certain depth already. So yeah, the scheme starts complicating itself. Another question they address is like, can we just vaporize the threat with enough nuclear weapons instead of just fragmenting it? Maybe if we turn it into a cloud of gas, it would be fine. Well, they make some calculations with all the materials coming in asteroids and the energy required to turn them into gas, and it would require a total of 320 gigatons, which is like 50 times the entire world arsenal of nuclear weapons. So we don't have the capability. And even if we had, if we could do this, but there was not enough time for the cloud to avoid Earth, the consequences due to the atmospheric heating of all this hot gas hitting our atmosphere would be also catastrophic. And this would happen, like it would be catastrophic even as I said before, like if these fragments, be in the form of gas or small rocks, hit the atmosphere, it's gonna be I'm gonna say hell. It's gonna be hell. Here's a plot of the atmosphere temperature rise versus the diameter of the impactor at different speeds. So the scenario they usually consider in this paper is like the impact is going to happen at 40 kilometers per second. So that's here. This is KT, means the boundary between the Cretacic and Tertiary periods, which is the extinction of the non-avian dinosaurs. Now we say KPG because it's the Paleogene instead of Tertiary. So it sounded better, KT, but it's KPG now. So the atmosphere temperature rise in kelvins means the same amount as in Celsius. So for the Cretacic Paleogene extinction event 66 million years ago, it's calculated that there was an atmosphere temperature rise of almost 100 degrees for a while. So this is an average, just for the impact energy and all the secondary impacts from all the material released and then coming back into the atmosphere. For our scenario, they calculate like 300 degrees hotter. So it's gonna cook humanity. If we let all the fragments impact, it's gonna be a catastrophe, even though the asteroid has been disrupted completely. If you remember this, they do this in the movie Deep Impact. Like, this is, I'm gonna say spoilers for a tiny bit. In the movie, they try to disrupt the asteroid and just they get a fragment that impacts on Earth, and the other one they completely vaporized it and destroyed it. But those fragments still hit the atmosphere. So in the movie, it's like a light show. But in reality, if the amount of mass of a 10-kilometer asteroid hits Earth, even though the atmosphere burns them up, it's gonna be a catastrophe either way. So we need to avoid this. So we need the fragment cloud diameter to be larger than the Earth by the time it reaches our planet. Here is a plot of the time before impact and the speeds of the fragments. This is the Earth diameter. So if we manage to deliver enough energy to the fragments, so once they are separated from themselves, they move at 1 meter per second, you would need to do it about 75 days before impact for them to have the same diameter as Earth. So if Earth was gonna be hit right on the edge and you move the cloud like the same diameter of the Earth, most of them are already gonna hit. So you need twice the size of that. So if the cloud was gonna be, if the asteroid was gonna hit like just on the edge, for the safety margin you need at least twice the size of the Earth for all the fragments to miss. Which means you would need 150 days for the interception time for 1 meter per second to work. So if you only have, say, a month, if the interceptor mission reaches the impactor a month before impact, you need at least 5 meters per second imparted into the fragments. And why do we say a month? Well, because the interception mission has to reach the impactor before doing its work and fragmenting it. And if the impactor is going towards Earth at 40 kilometers per second, well, we don't have ships that can deliver that amount of mass that fast. So they make some calculations, taking into account like when do we launch the mission, how fast the asteroid is moving, and to deduce when the intercept takes place. So for a 40 kilometers per second bolide speed, if the spacecraft is moving about 10 kilometers per second, the time to interception is gonna be a fifth of the time before launch. Of the time, before launch, I think. Sorry. I'm gonna give some examples because it's gonna be clear that way. So the calculations they do is like they don't take into account orbital mechanics for simplification. So this will be a more complex situation, but just to see the numbers how they would be is like if the impactor is going at 40 kilometers per second and the spacecraft is moving at 10 kilometers per second, then let's say we have 6 months of warning, so it takes 1 month to prepare and launch the mission. So 5 months since the launch until the impact. Then at those speeds, interception would take time 4 months later. So before impact, you have 5 months. You launch the mission then. 4 months later, it intercepts and fragments the asteroid. That gives you like in just 1 month, all the fragments will have to be separated enough to miss the Earth. If the asteroid is going slower, of course, if it's 20 kilometers per second, you can launch a smaller spacecraft, or maybe you can launch more payload in the same spacecraft. It would go slower because it needs to take more mass to the impactor. And it would take also the same amount of time, but it would intercept the asteroid closer to Earth. Now there's a question on how much of the energy of the nuclear devices can you really inject into the speed of the fragments, because this is the key on all of this. How much of the energy you deliver, of the capability you deliver, is gonna go into making the fragments move away from the trajectory of impact. For this, they use, as an example, this nuclear test, a thorax sedan nuclear test, in which a nuclear device about 200 meters underground was detonated. They calculate, given by the amount of the height the ground moved up before all of this breaking and sending things into the atmosphere and surrounding ground, they calculate that the coupling efficiency of this energy was only 2.3%. But they say this is a lower limit because Earth's gravity was adding a lot of pressure that the explosion would have to overcome, and this wouldn't happen in an asteroid in space. So they say, okay, at least 2.3% of the energy of the explosion would go into the fragments. And also, if that 100 kiloton explosion gives you a 390 meter crater, if the spacing of the charges in the 10 kilometer asteroid needs to be 400 meter, with these kinds of devices you would need, instead of 100 megaton, you would need 800 megaton for the entire surface of the asteroid to be disrupted. But yeah, this is only one data point, so they mentioned this to compare with real data, but there are more calculations needed to see how much coupling would be between the yield you deliver and the energy needed for this to work. And now, how do you deliver that amount of mass at that speed for the interception to take place? So they analyzed data for several launchers, and this would be SLS, which is the space launch system that the United States government is developing now. In fact, SLS-1 is already stacked for a launch this year if all goes well. And they compared that with future evolutions of the rocket and some other rockets, the Falcon 9 Heavy in different configurations and the Delta IV. So this plot, this is the characteristic energy, and what this means is, if it's 0, that amount of mass delivered by the rocket will reach the escape velocity, and that's it. So at infinite distance it would be at really low speeds. If it's lower than 0, that amount of mass will not leave Earth's orbit. It will be orbiting Earth, but you cannot deliver that into the asteroid. So this is the speed it would reach for this specific energy in kilometers per second. So if you need a spacecraft moving at 10 kilometers per second, so this is 100. This is the amount of the energy you need. So this corresponds, for the SLS-1B configuration, it's gonna be able to take less than 10 tons. The payload is gonna be less than 10 megatons of mass. Metric tons of mass. The SLS-2B configuration, which is a future evolution of the rocket, not existing yet, could take about 10, a bit more than 10 metric tons of mass. So we needed 25 metric tons, we calculated earlier, so it's gonna require at least 2 launches of this system. Now, they say, okay, if we launch from the moon, if we had these nuclear devices ready in orbit or on the moon, we could use smaller rockets which could be able to deliver the amount of mass, because from the speeds from the moon would be this. So 12 kilometers per second would be here, instead of reaching only like just a few kilometers per second with the same launcher. The moon's gravity is lower, so it's going to be more effective, but we don't have this capability from the moon yet, and we won't have it for many years to come. So this is an exercise like, okay, maybe it would be more efficient for us to put a lot of nuclear devices in orbit or on the moon in case a really big asteroid comes as a threat. Now these rockets, I'm gonna show some illustrations here. This is the SLS, the Space Launch System from the United States. This is the one that's already stacked to carry an Orion capsule around the moon. This is the cargo version. And yeah, this can put in low Earth orbit only about 27 tons. So the paper is talking about this version, which could put like 46 tons in low Earth orbit. Yeah, this one requires a lot of developments that we don't have yet, including an evolution of the solid rocket boosters, or even different size of boosters that we don't have yet. We have, and this already evolved from the Space Shuttle boosters. So yeah, it would need a lot of development that we don't have available yet. There's also, this is a chart on Wikipedia from all the super heavy lift launch vehicles. This is the SLS Block 1. This is the Saturn V that delivered Apollo to the moon. This is the Falcon Heavy, which is already in service. And this would be the SLS Block 2 that they're talking about. There's also a Starship, but they didn't include it in the previous plot because we don't have data yet on it. It hasn't launched anything to orbit yet. But this one, if you refuel the second stage in orbit, maybe just one launch would suffice to deliver this however many tons of mass you need for the interception mission to happen. With this one, you would need at least 2 launches. For smaller ones, you would need many launches, and it wouldn't be feasible. Now, the scenario of a 10-kilometer asteroid hitting us is really low probability. And also we have, if not all, most of these asteroids already detected in the solar system. So we know there's none of them, of the known ones, going to impact Earth in the near future. However, they bring attention to the scenario of the comet Neowise that 2 years ago appeared in the solar system. And it was discovered only 4 months before the closest approach to Earth, because this was not in the plane of the planets. This is a long period comet coming from the Oort cloud or so. It's gonna take it like maybe thousands of years to come back again. So yeah, these types of comets can appear as a surprise. This is the risk that we could have. In fact, the movie Don't Look Up features a comet instead of an asteroid because the science advisor, Amy Mainzer, which is part of the Neowise mission or service, she suggested a long period comet would be more probable to give us a surprise like this. So this particular comet was only 5 kilometers in diameter, which would be easier to disrupt and fragment than a 10-kilometer asteroid. However, we had less time to prepare. If this one was directed towards Earth, we would need a faster interception to reach the comet in time, and the fragment speeds would need to be higher to miss the Earth at that with the time we have before impact. However, it's smaller than a 10-kilometer asteroid considered for this scenario, but the speed with respect to the Sun when it was closest to the Earth was 53 kilometers per second, so it was faster. It had a higher kinetic energy, which, if you recall, goes with the square of the speed. The speed of the asteroid relative to the Sun when it was closest to Earth's orbit, not to Earth, was 70 kilometers per second. And relative to the Earth, if at that point the comet had crossed Earth's orbit, by the configuration, they were kind of going in the opposite direction, so the speed of the impact would be 100 kilometers per second. So yeah, it's a low probability event, but it could happen. So they use this example to warn, like, maybe we should be paying attention to these counteracting methods. And then they have some extra sections on the paper, which is like, okay, why so many movies use space shuttles? Could we use a space shuttle for a kind of mission of interception like this? And they point out, okay, so the space shuttle, when it was in service, it only reaches low Earth orbit, so about 600 kilometers only. If you were to intercept the impactor at that height, that means the interception would be only 15 seconds before impact, if the speed is 40 kilometers per second. So if you want to disrupt the asteroid so it misses the Earth from an interception mission at that height, you would need fragment speeds in the transversal direction of 1,000 kilometers per second, not meters per second. So the shuttle would need to carry a 160 billion megaton payload for this to work, and all be delivered. Like, no fragments going 1,000 kilometers per second down. They would all need to be really well aimed. So this cannot happen. And there's another movie in which they deflect an asteroid, in which they say, oh, this asteroid is the size of Texas. So yeah, that's about 800, 900 kilometers in size. That's Ceres. That's not a comet. That's a really, really big object. So the energy to disrupt this entire body would be 10 petatons of TNT, which is like 1 million times Earth's arsenal. In the movie, they split it in two, like really, really close before impact, and the two fragments miss the Earth completely, so everything's fine. But yeah, you will note that they also use shuttles. They are modified, but not by a lot. So yeah, these kind of movies, sometimes they are not very accurate. But in conclusion, no, wait, they have an extra section, because they, again, I really direct you to the Kurzgesagt video again. In the event 66 million years ago, 80% of the animals or so went extinct. And some species that survived were like, they could go on the ground or they were in the oceans. So they say, okay, if we have this situation in which we need to deflect or destroy a 10 kilometer wide asteroid that's going to impact Earth, we might need to build underground or underwater refugees, which would need to have multiple year food and water reserves. We might need to have in orbit or off-planet seed banks to recover afterwards when the world has been devastated. So they say, don't forget to look up, but also down. I really doubt we can build capability for the entire population, so this is going to be tricky. So in conclusion, what they say in this paper is that if we had a 6-month warning of an impact of a 10 kilometer object with this density at 40 kilometers per second, humanity could in theory defend itself with this method. The method would be an array of nuclear penetrators launched 5 months prior to impact, with an intercept 1 month before the impact, which would need to reach a fragmentation dispersal speed of 5 meters per second for the fragments to avoid Earth. And this is an unlikely scenario, but yeah, the Neowise comet could be a cautionary tale. However, like, maybe this whole paper is a way of directing attention to their proposed method for smaller asteroids. But yeah, they made a fun exercise, like, okay, what if the don't look up scenario takes place? However, yeah, they have some phrases in the paper that say, oh, in this scenario we hope logic would prevail and the nuclear testing is allowed to happen for us to develop the nuclear warheads that we need. So there are a few claims there that, yeah, a nuclear war among ourselves is more likely than this scenario to happen. So this method could have some important drawbacks. Also, as I'm not an expert on asteroid deflection, this nuclear proliferation, this scenario, I don't know how easier it would be to destroy the asteroid when compared to using nuclear devices to deflect the asteroid. Because for this asteroid, there are studies like that we had the DART mission already launched, which is gonna try to deflect an asteroid using the kinetic energy only. So it's gonna impact. Hopefully, some material will come out from the impact explosion, and that would impart enough speed for the asteroid. If we had a few years in advance, it could deflect it enough for it to miss Earth. In a scenario where the asteroid misses Earth, but in this case, it's not a threat. The asteroid that's going to be hit. It's just a test. So yeah, for really tiny asteroids, maybe just walking it with a probe is going to be enough. But for 10-kilometer wide asteroids, you see the charts of the method required and the energy and impact. We would need nuclear explosions to push the amount of material out so that the conservation of momentum drives the asteroid in the opposite direction. So yeah, I don't know how much easier that would be compared to the total disruption that they propose in this paper. But yeah, it was interesting to read. Hope you found it interesting too. And if you have any questions, you can drop them in the comments, or if you have anything to complain about. I'm also on Twitter with the handle name Dark Sapiens. And yeah, see you next time if I do another thing like this. Bye.